Let's dive into some JavaScript fundamentals first. Can you explain closures in JavaScript? Provide a practical example, perhaps emulating private variables, and discuss potential memory leak concerns associated with closures and how you'd mitigate them.
Certainly, a closure in JavaScript is essentially a function bundled together with references to its surrounding state, its lexical environment. This means an inner function retains access to its outer function's scope, like variables and parameters, even after the outer function has finished executing. A practical example is creating private variables or methods, often seen in the module pattern. For instance, you could have a function createCounter that declares a private count variable. It would return an object with methods like increment and getCount. These inner functions form closures over the count variable, allowing them to access and modify it. However, the count variable itself wouldn't be directly accessible from outside the returned object, effectively making it private. Regarding memory leaks, closures can cause issues if they unintentionally keep references to large objects or variables in the outer scope alive longer than needed. If an inner function, the closure, is still referenced somewhere, perhaps as an event listener or callback, it prevents the variables it closed over from being garbage collected. To mitigate this, you should be mindful of what variables are captured and avoid holding onto large data structures unnecessarily. If possible, explicitly set large outer variables to null if they are no longer needed by the closure. Crucially, ensure that closures used as event listeners or callbacks are properly removed when they are no longer needed, for example by removing event listeners when a component unmounts.
Excellent explanation, covering both the utility and the potential pitfalls. Now let's talk about asynchronous operations. Describe the JavaScript event loop mechanism. Explain the roles of the call stack, the macrotask queue or callback queue, and the microtask queue. How does process.nextTick fit into this specifically in Node, and what are its priority implications compared to microtasks like promise callbacks?
JavaScript is single-threaded, executing one piece of code at a time using a call stack. To handle asynchronous operations like I/O, timers, or network requests without blocking this main thread, JavaScript uses the event loop mechanism. Here's how it works. The call stack is where synchronous code execution happens. When an asynchronous operation like setTimeout is initiated, it's handled by browser web APIs or Node's underlying C++ APIs, often via libov. The JavaScript engine continues executing synchronous code. Once the asynchronous operation completes, its callback function is placed in the macrotask queue. Examples include callbacks from setTimeout, setInterval, I/O operations, and UI rendering. There's also a microtask queue, which holds callbacks for tasks needing higher priority, primarily promise resolutions, then, .catch, finally, and queue microtask. The event loop continuously checks if the call stack is empty. If it is, it first processes the entire microtask queue, executing all microtasks. Only after the microtask queue is empty does it take one task from the macrotask queue and push it onto the call stack for execution. Now, process.nextTick is specific to Node. Callbacks scheduled with it reside in their own nextTick queue. This queue is processed immediately after the current operation completes and before the event loop continues, specifically before processing the microtask queue and definitely before any macro tasks like I/O or timers. Therefore, process.nextTick callbacks have the highest priority, even higher than promise callbacks. Microtasks. Overuse can starve the event loop, so it's used for specific cases like ensuring operations happen before the event loop continues or breaking up long computations.
Very thorough. Understanding that priority difference between nextTick and microtasks is key in Node. Let's move on to another fundamental concept, the this keyword. Explain how this works in JavaScript. Describe how its value is determined in different contexts: global scope, regular function calls, object methods, constructor functions, arrow functions, and event handlers. Also, touch upon how .call, .apply, and .bind can be used to explicitly set its value.
The value of this keyword in JavaScript is determined by how a function is called, its invocation context, not where it's defined. In the global scope, this refers to the global object, window in browsers, global in Node, though it's module.exports in Node modules. In strict mode, it's undefined globally. When a function is called as a standalone function, this usually defaults to the global object, but it's undefined in strict mode. When a function is called as a method of an object, like objMyMethod, this refers to the object the method was called on, which is obj. When a function is used as a constructor with a new keyword, this refers to the newly created instance. Arrow functions are different. They don't have their own this binding. They inherit this lexically from their surrounding scope at the time they are defined. This is useful for callbacks within methods, where you want to retain the method's this context. In DOM event handlers, this is typically set to the element that triggered the event, unless an arrow function is used as the handler, in which case it retains the this from the enclosing scope. You can explicitly set the value of this using .call, .apply, and .bind. Both .call and .apply invoke the function immediately, setting this to the first argument. .call accepts subsequent arguments directly, while .apply accepts them as an array. .bind, however, doesn't invoke the function immediately. It returns a new function where this is permanently bound to the provided value. Any additional arguments passed to bind are prepended to the arguments passed when the bound function is eventually called. This is very useful for creating callbacks with a specific this context. Okay.
Perfect. Now let's shift focus specifically to Node. Node is often described as single-threaded. How does it actually achieve concurrency and handle numerous I/O operations efficiently without blocking? Explain the roles of libov and the thread pool in this architecture.
That's a great point. While JavaScript execution in Node runs on a single main thread, its concurrency model relies heavily on non-blocking I/O and the event loop orchestrated by the libov library. Node executes your JavaScript on one main thread which manages the event loop. For I/O operations like network requests or file system operations, Node uses asynchronous, non-blocking APIs. Instead of waiting, it initiates the request, registers a callback, and the main thread continues executing other code. libov is a C library providing the core asynchronous I/O functionality. It interfaces with the operating system's asynchronous mechanisms to handle these I/O operations efficiently off the main thread. libov manages the event loop and integrates completed I/O results back into the Node event queue. While most I/O is handled asynchronously by the OS via libov, some operations are inherently blocking or CPU-intensive, like certain synchronous file operations, DNS lookups, or cryptography. For these, libov maintains a small, fixed-size thread pool, usually 4 threads by default. Node offloads this blocking work to a thread from the pool, preventing the main JavaScript thread and event loop from being blocked. Once the task completes in the thread pool, libov queues the corresponding callback for execution by the main thread via the event loop. So Node achieves concurrency not through multiple JavaScript threads, but by delegating I/O and some blocking operations to libov and its thread pool, allowing the single main thread to remain responsive via the non-blocking event loop model.
Excellent detail on libov and the thread pool. Staying with Node, can you explain the differences between child_process.fork and child_process.spawn? Describe specific use cases where you would choose one over the other.
Both fork and spawn from Node's child_process module create child processes, but they differ significantly. Child_process.spawn is more general purpose. It launches any external command or executable in a new process, not necessarily a Node script. Communication happens via standard I/O streams, stdin, stdout, and stderr. You pipe data in and listen for data out. It generally has lower overhead. Use cases include running system commands like ls or git, executing non-Node scripts like Python, or streaming large amounts of data to/from an external process. Child_process.fork, on the other hand, is specifically designed to spawn new Node processes. It runs a specified Node module in a separate V8 instance. Crucially, it automatically establishes an IPC interprocess communication channel between the parent and child, allowing you to send JavaScript objects back and forth using .send and listening for message events. It has slightly higher overhead due to the V8 instance and IPC channel. Use cases include distributing CPU-bound tasks across multiple cores in Node to avoid blocking the main event loop, creating worker processes that communicate results via messages, or running parts of your Node application in isolation. Essentially, use fork for node-to-node communication and parallel processing within your application. Use spawn for executing external commands or interacting with non-node processes via standard I/O streams.
Clear distinction. Let's talk about Express. Explain the concept of middleware in the context of Express. How does the order of middleware registration matter? Provide an example of a simple custom middleware function, perhaps for logging incoming requests.
Middleware functions are the backbone of Express applications. They are functions that have access to the request object, rec, the response object, res, and the next function in the application's request-response cycle. Middleware can execute code, modify request/response objects, end the cycle by sending a response, or call the next middleware using next. The order of middleware registration using app.use or app.method is crucial. Requests flow through the middleware stack sequentially. Middleware registered earlier executes before middleware registered later for a given path. This is vital for tasks like authentication, check credentials before proceeding, logging, log before handling, or data parsing, parse body before accessing requeue.body. If a middleware doesn't call next or send a response, the request hangs. For example, a simple request logging middleware might look like this. A function request logger takes rec, res, and next as arguments. Inside, it could log the current timestamp, the request method, request method, and the request URL, request res.original URL. Then, crucially, it calls next to pass control to the next middleware or route handler in the stack. You would register this middleware using app.use, request logger, before defining your actual route handlers like app.get. This ensures every request gets logged before being processed by its specific route.
Good example. Finally, for this section, let's discuss API design. Describe the key principles of RESTful API design. How do you typically handle aspects like versioning, authentication, and error handling in the REST APIs?
REST, representational state transfer, is an architectural style for designing networked applications, primarily web services. Key principles include client-server architecture, separation of concerns, statelessness, each request is self-contained, server doesn't store client context, cacheability, responses define if they can be cached, layered system, intermediaries like proxies don't affect the request/response, and crucially, a uniform interface. The uniform interface includes resource identification using URIs, like users 123, resource manipulation through representations, clients interact via representations, commonly JSON, self-descriptive messages, using standard HTTP methods like GET, POST, PUT, DELETE, patch and appropriate status codes, and HATEOAS, hypermedia as the engine of application state, where responses include links to related actions/resources. Handling specific aspects. For versioning, common strategies are URI versioning, /API/v1/users, custom request headers, accept version v1, or using the accept header, accept application/vnd.company.v1 plus JSON. I often prefer URI versioning for its clarity. For authentication, stateless methods like JWT, JSON Web Tokens, sent in the authorization, bearer header are very common. OAuth 2.0 is standard for third-party authorization. Authorization, what a user can do, often involves role-based or attribute-based access control implemented in middleware. For error handling, use standard HTTP status codes, 2XX for success, 4XX for client errors, like 400 bad request, 401 unauthorized, 404 not found, and 5XX for server errors, 500 internal server error. Provide clear, consistent JSON error messages in the response body, including an error code and message, but avoid leaking sensitive details.
That covers the backend and core concepts well. Let's move to the front end and databases. Let's talk about React. Explain the purpose of the use memo and use callback hooks. Provide examples of when you'd use each, discuss the performance benefits, and importantly, highlight potential downsides or scenarios where misusing them could actually be detrimental.
Use memo and use callback are React hooks for performance optimization through memoization. Use memo memoizes the result of a function call, a value. It recomputes the value only when its dependencies change. You'd use it for computationally expensive calculations, like filtering a large list, to avoid running them on every render if inputs haven't changed. For example, const expensive value equals use memo equals greater than calculate expensive value, prop E, prop B. The benefit is avoiding costly recalculations. The downside is the overhead of memoization itself. Using it for trivial calculations can be slower. Also, incorrect dependencies can lead to stale data or negate the benefit. Use callback, on the other hand, memoizes the function definition itself. It returns the same function instance between renders unless dependencies change. Its primary use case is passing callbacks as props to child components optimized with React.memo. Without use callback, a new function instance is created on each parent render, causing the optimized child to re-render unnecessarily due to referential inequality. For example, const handle click equals use callback equals greater than do something, dependency value. The benefit is preventing unnecessary child re-renders. Downsides include the overhead, similar to use memo. Using it for functions not passed to memoized children often provides no benefit. Incorrect dependencies can lead to stale closures where the function references old state. It's crucial to use these hooks as optimizations after identifying performance bottlenecks, often using the React DevTools profiler, rather than applying them everywhere by default.
That's a very balanced perspective, emphasizing profiling and avoiding premature optimization. Now let's discuss state management. Describe the concept of lifting state up in React. When is it necessary? Discuss its trade-offs and compare it with alternatives like the Context API and state management libraries such as Redux or ZooStand. In what scenarios would you choose each approach?
Lifting state up is a core React pattern for sharing state. When multiple components need the same changing data, you move the state to their closest common ancestor. This ancestor manages the state and passes it down via props. If children need to update the state, the ancestor passes down callback functions as props too. It's necessary when sibling components need the same state or a child needs to update state affecting a sibling or parent, maintaining a single source of truth. The trade-off is potential prop drilling, passing props through many intermediate components that don't use them, making components less reusable and refactoring harder. The ancestor can also become overly complex. Alternatives include the Context API. This avoids prop drilling by providing a way to pass data down the tree without manual prop passing. You use a provider and consumers access the value via use context. It's best for global data that doesn't change frequently, like themes or auth status. However, frequent context changes can cause performance issues as all consumers might re-render. State management libraries, Redux, ZooStand. These provide a centralized store external to components. Components subscribe to state slices and dispatch actions to update state via reducers in Redux. They're ideal for large, complex apps with significant shared state, complex update logic, or when state is needed by distant components. They offer better organization and debugging tools but add boilerplate and complexity, possibly overkill for small apps. ZooStand is often seen as a simpler alternative to Redux. My approach is, start with local state, lift state up for closely related components, use context for low-frequency global data, and adopt Redux/ZooStand when global state gets complex or prop drilling becomes unmanageable.
Good breakdown of the different state management strategies and their appropriate contexts. One more React question. Explain the concept of the virtual DOM. How does React use it during the reconciliation process to update the actual DOM efficiently?
The virtual DOM, VDOM, is a programming concept where a virtual representation of the UI is kept in memory, essentially a lightweight JavaScript object tree copy of the real DOM. React uses it for performance optimization because manipulating the real DOM directly is slow. The process, called reconciliation, works like this. When a component's state or props change, React creates a new VDOM tree. It then compares, diffs, this new VDOM tree, with the previous one stored in memory, using efficient algorithms to identify the specific changes. React determines the minimal set of operations needed to update the real DOM to match the new VDOM. Finally, it applies only the specific batch changes to the actual browser DOM, like changing an attribute or updating text content instead of re-rendering large parts. This is much faster because manipulating JavaScript objects, VDOM, is quicker than direct DOM manipulation, the diffing is efficient, and batching updates minimizes costly interactions with the real DOM. This allows React to achieve high performance even with frequent UI updates. JSX helps create these VDOM elements more easily.
Excellent. Let's switch to databases. Compare and contrast SQL relational and NoSQL databases. Discuss key differences in terms of data structure, schema flexibility, scalability, and consistency models. Crucially, how does the CAP theorem, consistency, availability, partition tolerance, relate to these differences and influence the choice between them for specific use cases?
SQL and NoSQL databases differ fundamentally. SQL databases are relational, storing data in structured tables with rows and columns and a predefined, strict schema. They use SQL for querying and typically scale vertically, bigger server, though horizontal scaling can be complex. They prioritize strong consistency, usually adhering to ACID properties: atomicity, consistency, isolation, durability. NoSQL databases are non-relational and handle unstructured or semi-structured data using various models like key value, document, column family, or graph. They often have dynamic, flexible schemas. They are designed for horizontal scalability, more servers, and often prioritize base properties, basically available, soft state, eventual consistency, over strict ACID, offering tunable consistency levels. Query languages vary by database type. The CAP theorem states a distributed system can only guarantee 2 of 3: consistency, C, availability, A, and partition tolerance, P. Since network partitions, P, are inevitable in distributed systems, the trade-off is between C and A. Traditional SQL databases, when distributed, often prioritize consistency over availability, CP. During a partition, they might become unavailable for writes on some nodes to ensure consistency. NoSQL databases explicitly embrace this trade-off. Many prioritize availability and partition tolerance, AP, accepting eventual consistency, like Cassandra, DynamoDB. Others might prioritize consistency and partition tolerance, CP, sacrificing availability during partitions, like MongoDB in certain configurations, HBase. So choose SQL when strong consistency, ACID, is paramount. Data is structured, complex joins are needed, and vertical scaling is sufficient, or horizontal complexity is acceptable, e.g. financial transactions. Choose NoSQL when high scalability/availability are critical, the schema is flexible/evolving, data is unstructured, and eventual consistency is acceptable, e.g. social media feeds, IoT data, caching. The choice depends heavily on the application's specific needs regarding structure, scale, and consistency, mapping directly to the CAP theorem trade-offs.
That's a comprehensive comparison. Let's move into system design. Okay, let's design a simplified URL shortening service similar to tinyURL or bit.ly. Walk me through how you would approach the requirements gathering, API design, data modeling, considering the SQL versus NoSQL trade-offs we just discussed, hash generation and collision handling, and strategies for scaling this service to handle high read and write traffic. What are some potential bottlenecks you foresee?
Okay, designing a URL shortener. First, requirements gathering. Functionally, users input a long URL and get a unique short URL back. Accessing the short URL redirects to the long one. Non-functionally, we need high availability, especially for redirection, low latency redirection, scalability for potentially billions of URLs and high read traffic, and durability. Links shouldn't disappear. Let's assume no custom URLs or expiration initially, and no analytics needed for the core design. For the API design, a simple REST approach works. A post/API/v1/shorten endpoint takes long URL and returns short URL, http://short.ly/ab3xyz on success 201 created. A get/shortcode endpoint like http://short test.ly/ab3xyz closing parenthesis performs a 301 or 302 redirect to the original long URL, or returns 404 if not found. Data modeling requires storing the mapping, shortcode, unique key to long URL, plus may be created at. Comparing SQL versus NoSQL SQL, like PostgreSQL, offers ACID compliance, but horizontal scaling can be harder, and generating unique IDs might bottleneck. NoSQL, like a key-value store, Redis, DynamoDB, offers excellent scalability and low latency for key lookups, perfect for the read-heavy redirection. Fitting an AP model, availability, partition tolerance, well, given the high read volume and scalability needs, I'd lean towards a NoSQL key-value store for the core mapping. For hash generation/short code, instead of hashing the long URL prone to collisions, a better approach is generating a unique numerical ID using a distributed ID generator like Snowflake or a dedicated counter service to avoid DB sequence bottlenecks, and then converting this ID to a base 62 representation, a ZZ09. This guarantees unique, short URL safe codes and avoids collision handling complexity. We store the mapping, shortcode to long URL. Scaling strategies, the read path, get/shortcode, is critical. Use load balancers to distribute requests to stateless redirector services. Implement aggressive caching, distributed cache like Redis/Memcached, for shortcode to long URL mappings to minimize DB hits and latency. ACDN could cache redirects at the edge. The database itself should be a scalable NoSQL key-value store, possibly with read replicas. The write path, post/shorten, is less frequent but needs reliability. Use load balancers, application servers to generate ID, convert, store, populate cache, and ensure the database, potentially sharded eventually, and the unique ID generation service are scalable and fault-tolerant. Potential bottlenecks include the unique ID generation service, if centralized, database write contention, cache misses forcing load back onto the database, and ensuring redundancy at all layers, load balancers, servers, cache, DB, to avoid single points of failure.
That's a solid approach, covering the key trade-offs and scaling considerations. You clearly identified the read-heavy nature and the importance of caching. Let's move on to testing and DevOps. Describe your approach to ensuring code quality in a full-stack application. How do you integrate different levels of testing, unit, integration, and end-to-end, E2E, into your workflow? What tools, like Jest, Cypress, or React testing library, do you prefer, and why?
My approach follows the testing pyramid, a wide base of unit tests, fewer integration tests, and even fewer E2E tests. For unit tests, which verify the smallest code units in isolation, I prefer Jest as the runner/assertion/mocking framework. On the front end, React, I combine Jest with React Testing Library, RTL. RTL encourages testing component behavior from a user's perspective, making tests more resilient. We test rendering, state changes on interaction, and prop handling. On the back end, Node. Jest is great for testing utilities, middleware, controllers, or service layers, mocking dependencies like DB calls. For integration tests, verifying interactions between units, on the front end, we might test how components work together within a feature using RTL/Jest, possibly mocking API calls with tools like Mock Service Worker, MSW, for realistic simulation. On the back end, we test API endpoints interacting with services, middleware, and a real test database, often using Supertest with Jest to make HTTP requests. For end-to-end E2E tests, simulating real user workflows across the stack, I prefer Cypress. It runs in the browser, offers great debugging, time travel, auto-waiting, and tends to be more stable than Selenium-based tools. E2E tests cover critical paths like login, registration, and core feature usage. In the workflow, tests are written alongside features. Unit and integration tests run locally and in the CI pipeline on every commit/PR. E2E tests also run in CI, typically before deployment to staging or production.
Good overview. How do you specifically leverage CI/CD pipelines to enforce these quality standards? How would you integrate automated linting, testing, and potentially code analysis tools into the pipeline?
CI/CD pipelines are crucial for automating quality gates. Typically, a pipeline triggers on push or pull request creation. An early stage runs linters, like ESLint, and formatters, like Prettier, to check code style and basic syntax. Failure stops the pipeline. Next, unit tests, jest4tl run, potentially generating coverage reports. Failure stops the pipeline. Then, integration tests run, possibly requiring setup like a test database via Docker Compose and CI. Failure stops the pipeline. If tests pass, the application is built, front-end assets compiled, back-end packaged, maybe into a Docker image. Optionally, static code analysis tools like SonarQube can run to check for code smells, vulnerabilities, etc., potentially failing the build based on quality gates. E2E tests, Cypress, often run next, usually against a deployed instance in a staging environment. Failure here typically prevents production deployment. Finally, if all stages pass, the pipeline deploys the application, continuous delivery/deployment. Code reviews are integrated, usually at the PR stage before merging. Pipeline results, linting, tests, coverage, inform reviewers. This automated feedback loop catches issues early, enforces standards, prevents regressions, and increases deployment confidence.